Okay. You're on.
Your Honor.
Your Honor? Your Honor, Your Honor. All right, so this is Thursday, December the 3rd. Nice. Oh, that means I got to write something for somebody. Multivariable Calculus, Math 265. It's 11:40. And today we're going to continue our discussion of surface integrals. And hopefully get to Stokes' theorem. And if we hustle at the end, we might be able to get to the divergence theorem. Divergence theorem, which is also known as Gauss's theorem, because Gauss proved it. At least he's one of the people.
Hey, I see him.
Okay. So yesterday we defined a surface integral, so that tells us what happens if you have some surface in R3 and you have a function defined on that surface and you want to integrate that function. So you define this surface is called S. You the surface integral of a function. It was defined as this limit. So I'll just put, I think what we wrote down yesterday. Okay, but it's just the same flavor as every other integral we've ever defined. And just like with every other integral we've ever defined, we don't really want to compute it using the limit, so we want to write down a better formula. To do that, we need a little more sophisticated parameterization for the surface. So in terms of, say, a U and a V, this is like a U and a V plane, we might parameterize it the following way. It eats a U and a V coordinate, and it's going to spit out a function with three variables, or three components, which are dependent on U and V. And that's why I use U and V here, is because I also want to use X, Y, and Z for my components. Okay, so if we start with a parameterization of this surface, given by these components, then it's going to turn out that the surface integral we can rewrite as a double integral. And so the double integral will be given by, well, I guess I should put my little vector here, because that R is a vector function. This should be f of R of uv. And then this looks a little weird, and I'm not going to give you hardly any details today, so it's going to have to look a little weird. You take the partial derivative of R with respect to u. Okay, so that means each component you take the partial derivative. So this gives you a new vector function. It looks like xu, y sub u, z sub u. You're taking the partials in each component. And then you're going to take the cross product of the same construction but with v. And the reason you're doing this is because this is giving you somehow the area of those. Remember when we broke this thing up, we partitioned it up, and we got little rectangles, or at least kind of curved rectangles. And this is helping to give you that area. So that's where that's coming from. And then this is dA. Let's see. Yeah. So there's some hypotheses on here that we need. So first, I guess x of uv and y of uv are continuous. And then these partial derivative vectors, RU and RV. not the one you drive around with your grandmother in the back. So RU and RV should be non-parallel. Oh dear. And non-zero in the domain D. So, what is D? I didn't mention D this whole time. So remember originally when we defined the surface integral, underneath the surface we wrote down a rectangle and we broke that up. Right, and then we projected all those things back up onto the surface. This is the D. So you're taking the double integral over this region here, right, which is in the xy plane. And, well, the way I've drawn it, this D is a rectangle, but you should note all these actually work even if D is not a rectangle. So D does not have to be a rectangle. Just like before when we did double integration. You started by defining it over a rectangle, but in the end you don't have to let it be one. Okay, so now comes a little computation. This is supposed to be inspired by another example that we did, which was, remember when we computed the volume of a sphere? Remember I came up and I made this big thing. We were in the 11th floor for that one, and I made this big thing. I said, now how do you know that the volume of a sphere is 4/3 pi r cubed? And I said, oh yeah, probably your 4th grade teacher told you, even before that, right? And then he said, oh yeah. And I said, well, how did they prove it to you? And he said, well, of course they didn't prove it to me. He said, well, here's how they should have proved it to you. Yeah, we did a triple integral to take care of it. Well, what about the surface area of the sphere? What is the surface area of a sphere with radius r? So this is another thing that they actually taught you in 4th or 5th grade. And I'm sure they definitely did not prove it using surface integrals. It kind of in China it's a little different.
I don't know from China, but the proof it is in the book.
Yes, the proof is in the book. Oh, you mean your 5th grade text?
I mean, they prove the formula is in the book, not just made up.
All right, so what is it? It's 4 pi r squared. How can you always remember it? The surface area is the derivative of the volume.
Oh.
You know? Or if you like, the volume is the antiderivative of the surface area. Because you think about this, right? What does integration do? You take some basic single variable. You take a curve, right? And when you compute the definite integral, that gives you the area under the curve. Okay. Well, what if you had a surface like this? Then somehow you'd think integration should give you the volume trapped by the surface. So if you know the surface area and you anti-differentiate it, you should get the volume. And right, remember the volume of a sphere is 4/3 pi r cubed. Take the derivative, 4 pi r squared. It's a handy way to remember it. Try telling a 4th grader though, well, easy to remember it. It's just the derivative. Some mnemonics require a lot more knowledge than others. Okay. So how do we get the surface area of a sphere? Well, first let's write down the equation of the sphere. We might as well do it centered at 0. So it looks like x squared plus y squared plus z squared equals r squared. And, well, what does this surface integral tell you? Well, you take some surface, and at every point you're evaluating the function, seeing what value it gets. And then you sort of add up all those values, right, in the way that we usually do with integration. Fine? Well, what if we evaluate just the function 1 at every point? Well, then for every point on here, we just get the value 1. So in fact, what you should be getting when you compute the surface integral is the surface area times 1, right, which is the height off of the surface. Right? So what you might think of is take a sphere and at every point move one away and then draw another sphere. And then what's the volume that you're getting? Right? And that volume actually should be exactly equal to the surface area. It's very similar to when you say take a rectangle and then ask what is the volume of this parallelepiped. Ooh, looks terrible. I should go down a little bit. Uh-oh. In any case, how do you do it? We take the area of the base times the height. And if the height is 1, what's the volume?
The area of the base.
It's just, as far as if you forget the units, it's just the area of the base. The same thing works here. If you take the function 1, right, which is just telling you the height, it's basically just how far off the surface somehow it's going, right, or what, not off the surface, but how high it's going. Right? You're just getting the area of the surface times the height. Of course, normally functions change a lot, so times the height doesn't mean anything. It's changing. But when it's a constant function, it really does mean just times the height. And we've seen this before. If you integrate and then just put a 1 as your function, right? When we did the triple integral, that gave you, right? If you did triple integral over a surface, it just gave you the easy one was a double integral, right? You take some region, and then you just do the double integral of the region with the function 1, that just gives you the area of that region. So this is just a souped up version of that. So to compute the surface area, say our sphere is given by the label S2. This is, I know this is not the right number. It's not a two-dimensional object, is it? But it's still called S2. Circle is called S1. And the sphere is called S2. So the surface area of S2, so A here means the surface area, should just be the double integral, not double integral, the surface integral of the constant function ds. Okay. So if we use this formula to the right, we can rewrite this as an honest-to-goodness double integral, right, where d here is going to be the domain captured by the surface. So okay, the surface is S. What's d? D is everything, right, the inside as well. It's like a bowling ball, right? D is the, S would just be a hollow ball, D is the whole bowling ball. So we integrate over D. The function is just 1. There's no function lying around. And then you need to put down, well, okay, we need to actually have the RU and RV. Since we don't know what those are immediately, let's just leave it. So I'm just copying this formula here, where this is 1. Okay. What do I want to do? I guess I want to transfer into spherical coordinates. Yeah. So since when I have a sphere, it's a good idea to switch to spherical coordinates to do the double integral. I think that's a good way to say this. So I guess let me, because we're always doing rho in our spherical coordinates instead of r, I'm just going to change it up in the middle here and just assign rho to be r, right? For the purposes of doing spherical coordinates switch, right? And we know that, okay, you guys have to help me here. When we go to spherical coordinates, x is rho what is it? Cosine phi sine theta? Or we need a good way to memorize this. There's a picture, of course, but we'd rather just have a good mnemonic. I think I have it backwards. I think it should be sine phi cosine theta. Now, I know once you get x, it's easy to get y. You just turn all the c's into s's. And then, what's the z? The z is rho, is it sine phi? Or sine theta? Sine phi, I think. No, cosine phi. And so here, phi goes from 0 to pi, and theta goes from 0 to 2 pi. So that's our switch. So before Monday, from this next Monday, you should of course memorize those. Okay, so the parameterization for the surface we fixed rho, right? So it's not, we don't need to worry about rho. Yeah, we fixed rho. That's given. Right, what is the parameterization? So how do we describe this sphere? Well, it's x, y, z. Yeah? You have all these x, y, z points. That's what it is. And we just showed you how to write down x, y, z. So it's rho sine phi cosine of theta. That's the x coordinate. The y coordinate is rho sine phi sine theta. And the z coordinate is rho cosine of phi. Okay. So this formula up here says we need to compute the, well, instead of u and v, we've switched everything into phi and theta. So we need to compute r phi and r theta. And then we need to compute the cross product. So let's see, r phi is, well, we need the partial derivative with respect to phi. So with respect to phi, this becomes rho cosine phi cosine theta, rho cosine phi cosine theta minus rho. The part where we
went to
here?
Nope.
Here.
Yep.
I'm taking the partial derivative with respect to phi.
Okay.
So in this, and you do component by component.
Okay.
So the sine of phi becomes a cosine of phi, the sine of phi becomes a cosine of phi, the cosine of phi becomes a minus sine of phi.
Okay.
And then I also need the one with respect to theta. And that'll be minus rho sine phi sine theta, rho sine phi cosine theta, and then 0.
So change u and v to
Phi and theta. Yeah. Okay, so now I need to compute the norm of the cross product. So let me compute the cross product. Oh, I just realized I'm on the wrong board.
Did you like the other one better?
Oh, I like that having to erase.
Yeah.
Okay, so to compute the cross product, we write down I, J, K. Oh dear, we're going to need a lot of room. So first we write down the, it's not u, it's phi. And it's not v, it's theta. And the phi is, okay, we'll go rho cosine theta cosine phi, and then rho cosine phi, wait a second, We have these backwards. Phi theta. Is it really the same in both? Yeah, okay. And then minus rho sine theta. Phi. You gotta watch me here. And then minus rho sine phi sine theta. And then rho sine phi cosine theta. And then 0. And can you imagine how big this is if you write out sines and cosines? Okay, so I'm going to save some time here and tell you that if you compute this determinant, it actually is not so bad. There's a lot of cancellation that goes on. And you have to use that sine squared plus cosine squared is 1. But if you use that, you get rho squared sine phi. Not a huge surprise, actually. It's very similar to the Jacobian, yeah? Okay, so I don't know why I have this with me. The surface area of A2 is given by the double integral of rho squared sine phi. dA. And, well, we know what d is. D is just the inside of this ball. It's given in terms of phi and theta by phi running from 0 to pi and theta running from 0 to 2 pi. And then the radius is allowed to, well, the radius is what it is. So, the radius is fixed, so we pull the radius out. And we integrate 0 to pi, 0 to 2 pi. I'll write it out now. Sine of phi, d theta d phi. And, well, I can break this up into two different integrals, because there's the phis and the thetas are separate. In fact, there's no thetas. So this is rho squared, integral 0 to pi of sine of phi, d phi, integral 0 to 2 pi of d theta. Sine of phi, the integral is minus cosine from 0 to pi. So minus cosine of pi, cosine of pi is minus 1, so minus cosine of pi is 1. And then cosine of pi, cosine of 0 is 1, so you get a minus of minus minus 1 is 2. It is 1, but 1 plus 1 is 2. So this is times 2. And then this is just 2 pi, because it's the length of the interval. So this is 4 pi rho squared, but rho is equal to r. So 4 pi r squared. So that's what we want. The area, surface area of the sphere was 4 pi r squared. All right.
Let me change it.
Now we got to start hustling a little.
Thank you.
So just as we did with line integrals, once you define the line integral of a scalar function, you then want to define the line integral of a vector field. Well, we've defined the surface integral of a scalar function. Now we want to define the surface integral of a vector field. Okay, to do so, let's see, I think, well, I don't think I do need that. I just need to give you some terminology, and this is going to be very quick. All right, we're not going to get to a lot of details of it. Let's say I have a sphere. Okay? At every point on the sphere, I can draw the unit normal vector. If I do that, then you should complain. Why should you complain? If I tell you that this coming out, right, the board is the unit normal vector at that point, what should you object to? This is supposed to be at every point I'm doing this, right? If I go over here, there's 9. Why should you object that this is the unit normal vector? Okay, what is it? Unit. Unit shouldn't mean anything really bad. It just means length 1. Okay, so there's no real problem with that. What did normal mean? Remember we defined this yesterday. It should be perpendicular to the tangent, right? Okay, so for instance, you might have a tangent vector going this way. There, okay, that's definitely perpendicular to it. What's the problem calling it the unit normal vector?
Only one. Only one.
The only one. Is there another one? Which way could I go? I could go this way, right? I could go inside. If I was sitting on the sphere, I can either point away from the center of the sphere, or point out basically, not away from the center, but point out, or I could point in. Right? At any given point, I can point out, or I could be pointing in. So there's no the unit normal vector. However, just as when we had closed curves, and we said, okay, if we traverse them this way, where the inside of the curve is on the left, we're going to call it positively oriented. We're going to do the same thing with a surface. If you're pointed away from the inside, that's the positive orientation, and if you point in, that's the negative orientation. Right? Now, there are some surfaces where you cannot do this. That is, you cannot make a choice which is consistent. What do I mean by consistent? Well, let's say I have to write down, for every point I have to write down a normal vector. And I all want them to be pointing in the same direction, in the sense that they all should be pointing away from something or towards something. Right? Now, let's say I point in this direction. If I have two points that are very, very close to each other, they should not be pointed, the normal vector should not be pointed in different directions. Right? If they're close, the normal vectors should be very close to each other. So if you define a whole vector function, it should be continuous. Right? Points that are really close to each other should, actually it's a vector field, they should give you vectors which are pointed very, very close to the same direction. But if you take, I don't even know if I can draw that. Has everybody in here seen a Mobius strip before?
A what?
A Mobius strip. Or more correctly pronounced, Möbius strip.
Yeah.
So you can all make one. What you do is you take a nice strip of paper, do a half twist. So just turn it over halfway, and then connect up the endpoints.
Oh, okay. Yeah.
Right? And what makes this little construction interesting? Well, for instance, if you take your pen and start drawing down the middle, right? If you take some strip of it and you start drawing like this, you keep going, you keep going, you keep going. Eventually you get back where you started. Okay, well that's no big deal. If you did that with a belt, right, that would work. If you drew a line around it. The difference when you do it with a belt is that you only get the outside, right? You miss the inside. With a Mobius strip, you get both sides. And the reason why you get both sides is because on a Mobius strip, there's only one side. You like to think, oh, there's two sides to the paper still. You can keep your hand moving without going around the edge, and you'll end up on both sides. At least both sides of what we originally called both sides. So now there's only one side. A Mobius strip is what is called a non-orientable surface. Very good. So you can construct one. The reason why it's called a non-orientable surface is because if you start drawing your tangent vectors, right, or your normal vectors, and you keep putting them in the same way, and you go all the way around, when you get back to the beginning, you're going to find they're pointed in the wrong way. They're pointed in the opposite direction as when you started. So you cannot make a choice of these normal vectors in a consistent way. with a Mobius strip.
The Mobius strip is twist on one side or two sides?
You just take one side and twist it,
One
yeah,
side.
so you can look at what it is. And start drawing on it, down the middle, and you'll see you get all the way around.
Did you do it?
Yeah? Here, when you're done with that, pass that up here. We'll show it to the camera. These things are really neat to start playing with. You start taking a pair of scissors, for instance, cut into the middle. Don't cut from the outside in. Just poke into the middle and start cutting around that strip. And when you cut it in half once, by doing that, I think what is it? You get, I think it's still one Mobius strip, or at least it looks like one. You cut it in half again, and you end up getting two Mobius strips that are chained together. It's really freaky. But a lot of weird things happen when you start talking about non-orientable surfaces. So Mobius strip is a non-orientable surface. Right? Which just means you cannot put normal vectors on it in a continuous, consistent way. But a sphere is an orientable surface. And if your normal vectors are all pointed away from the inside of the region, then we'll call it positively oriented and the like. But we actually don't, I mean, all we really need is that we have orientable surfaces. That's the key. So you can put these ends down in a consistent, continuous way. So here is the... It just... yeah.
I should staple it.
They, Mobius strips are cool, but they're not always very well behaved when you start pulling on them.
Wait, how do I? You should stay. Wait.
Yeah. There's half from yesterday. Yeah.
Okay, so here's what we need.
Yeah.
So we're going to let F be a, I think I want a continuous, yeah. A continuous vector field.
You want me to go on the details?
On an orientable surface. Yes. Okay, so it could be a sphere. So we can define the surface integral, and we're going to write f ds, and then we're going to put the little vector over the s here, like we did over the r. Anyway, here was the Mobius strip, which somebody took the time to actually draw on and saw that it got, well, actually they stopped halfway through writing on it. But if they kept going, you see it keeps going, and it goes on the inside, and around, and around, and back where you started. So that's very nice. There you go. Yeah. Nice Mobius strip. Non-orientable surface. When you have little nieces and nephews, you can make one of these for them. They'll just think it's the neatest thing in the world. You start, if you make one a little wider, it's easier to cut it twice in half. And then, just as they're really excited, mention to them, this is a non-orientable surface. And you'll feel like you're contributing to the future.
Wait, you cut it in half? What do you mean you cut it in half?
Not cut it this way. I mean, if you take the strip and you cut it this way, you just break it.
Oh.
No. What you want to do is poke a hole in the middle, and then cut along the...
Oh, so you have like two...
It'll end up... You do it twice.
Do it twice?
Do it twice. The first time... No, what happens when you do it the first time is you just get a bigger Mobius strip. At least it looks like one.
Oh.
And then when you do it a second time, if I remember correctly what happens, when you do it the second time, you get two Mobius strips, but they're chained like this.
Anybody got scissors? Let's do it now.
Now you're thinking this would have been a better, much cooler final project.
Something is getting complex.
Okay. So we're going to define this surface integral, although we're not. It's sometimes called the surface integral. It's also sometimes called the flux. F-L-U-X. And the way you can define it is we just take it back to being a real surface integral over a scalar function. So the way we do that is we take f, and we take the dot product with the unit normal vector field. Okay. So when you take this dot product of these two vector fields, you end up getting a scalar function. And then we know how to actually compute this, because that's what we did first. Okay. So I'll skip some of the details here and just say that this ends up equaling. So if, again, this surface encloses a region D, this ends up being the double integral over D of the dot product of F with the cross product of RU and RV, where again here R is parameterizing S. Right, and it's a function UV, U comma V. Okay, well I have, okay, let me give you, okay, would you rather just see the theorem, Stokes Theorem now, or would you like to see an example of this flux integral? So this is called surface flux integral. I don't know how interested you guys are in physics. So I could show you Gauss's law, for instance, and electric flux.
You choose an example.
Would you like to? Okay. So,
okay, lovely.
Just like with gravity, remember we had the gravitational vector field? At every point there's this pull of gravity on it. You have the same thing with electricity. You have an electrical field, right? At every point, if there's some electrical charge, every point gives you an electrical field. It gives you a
surface or flux. Yeah.
So let E be an electrical field.
Did you try it reverse?
And if we have a surface S, then the flux we can, of course, do into any. Oh, did I write E dot N? I just want E dot S. So we can take, for any vector field here, we can take the this flux integral, and so this one is, it's just the flux integral of E, and it's usually called the electrical flux. So Gauss's law, which I have to write down the condition here. So Gauss's law says the net charge enclosed by a closed surface. S. So what do I mean by closed surface? Same thing as a closed line. Right? There's an interior and an exterior. Right? A sphere is closed. Right? If you drew this surface, this isn't closed. There's no inside and outside. It doesn't split the region, space into two parts. Right? It doesn't fence off some region of space. Right? But if you oh shoot, that didn't even come out anywhere near what I wanted it. If I took this piece of paper and started closing things off, right? I pinched it at the ends, right? Okay, now I have this outside surface and there's an inside. You could hide something in there. Okay, there's an inside and an outside. It's a closed surface. It's closed off. It's like closing a box. Okay, so if you take the net charge enclosed by a closed surface S, so you're looking at some surface and you look on the inside and you want to know what's the net charge enclosed inside that surface. Gauss said that this equals, well, there's some constant, which is the permittivity of free space, something like this. I'm going to guess on this. I can't exactly remember what the constant is. I think it's the permittivity of free space. And that's just times the electrical flux. So it's some constant times the electrical flux. I have another example, which for time reasons I won't write down, but it basically is talking about if you have some surface and you have some body, right? And you look at you have the surface, and at every point in the body you have a temperature. Right? So you can find the temperature at that point. You can write down the rate of the heat flowing across that body, right? Because you might be the air is moving. That is also given in terms of a flux integral or surface integral. Right? It ends up just being the surface integral of the gradient of the temperature. So you take back the gradient vector field for the temperature function. And then you have to multiply by, again, a constant, which is like the conductivity of the air or something like this. Okay, so this is a terribly important integral in physics. Anytime you're dealing with heat flowing, electrical, anytime you have a vector field that shows stuff flowing and you want to measure the net amount of flow that's going over it, right? You're using the flux integral. So these are important. Okay, so now I want to give you Stokes Theorem, because no course in multivariable calculus could be complete without Stokes Theorem. And Stokes Theorem is just giving you another way to compute integrals. So what should I? Yeah, this is okay. Okay, so we're going to be dealing again with an S, right, which is going to be an orientable surface, and we want it to be nice and smooth, nothing really tricky going on. The surface maybe looks, like this. Right? There's some bend to it. Maybe it's better if I dot it for the bend. Okay, so you have some surface, that's your S, and then the boundary of S I'll call C, and this should be a closed curve, right? Should go all the way around the surface. Okay, and I'm going to assume that I have some vector field F, and I want, as usual, that the components of F should have continuous partial derivatives. Right, so they're kind of the usual technical hoo-ha. And Stokes' theorem is going to say that if you take actually just the line integral around C, that this is equal to the surface integral, or the flux integral, of the curl of F. Now, what's really neat about this is that it falls exactly into the same sort of pattern we've had the whole time when we're trying to prove analogs of the fundamental theorem of calculus. Right? So the fundamental theorem of calculus said that if you want to integrate over just a line segment, you have to take an antiderivative and evaluate it at the endpoints, which are the boundary of the line segment. When we talked about Green's theorem yesterday, we said if you want to do a line integral, before we did Green's, we did the fundamental theorem of line integrals, which said you just look at, right, you evaluate an antiderivative at the endpoints. Green's theorem did the same thing, only we ended up with a double integral, and we ended up evaluating along the whole boundary. Yeah. And this is saying the same thing. To compute, over here, this flux integral, you have to take an antiderivative, right? You think of the curl as a derivative, right? Because what is the curl, right? It's the gradient cross product f, but that gradient is taking partial derivatives. So you think of this as a derivative. To compute this flux integral, you end up taking an antiderivative and evaluating it on the boundary of the surface, right? S is the surface, C is the boundary of the surface. So it's exactly the same thing. They're all coming from the same tree here. Right? These are apples falling from the same tree. So this is nice because to evaluate the surface integral, you only have to evaluate a line integral. This is quite useful. Calvin.
Can you explain a little more the graph? Because I don't understand the graph.
Oh, so this is just a surface. Right? The same thing is like this. Just you use some wavy surface. Yeah? And you want to take the flux integral of a vector field over that surface. Okay, so I'm trying to integrate f, this vector field, over this surface. I want to compute the surface integral, which is what we were doing over here. And Stokes' theorem is saying, well, write down the boundary of S, it's this curve C, and if you want to, well, it actually turns out you're not computing the flux integral of f, but the curl of f, then you can actually just compute the line integral of C. Or alternatively, and this is often how it actually gets used, and this is similar to Green's theorem in that we actually used it going left to right. If you want to evaluate the line integral, you can treat it as a surface integral or flux integral, but you get to replace f with the curl. And as we saw with Green's theorem, the advantage of that is when you took derivatives, you sometimes simplify the vector field considerably. I remember we had those cool examples where when you took the partials with respect to y, for instance, all the x terms that were nasty died, and when then you did it with respect to x and all the nasty y terms died. The same thing can happen here. You can simplify the vector field by taking the curl. And so even though you're maybe taking a surface integral, which in principle sounds harder, because this function is much easier, the whole process is easier. I think Kaiwei left in the middle of the answer to his question.
You really have to go.
So I'll just let me just mention that if you take this surface and you actually just let it be something flat that sits in the xy plane, and then you take the unit normal vectors, just have them pointing up, then they're just k basically, right? The unit vector k. Then, well, if you compute this, you get it by computing that by Stokes' theorem. And computing this is the same thing as taking f and taking the dot product with the unit normal vector field, which is just k everywhere. But if you take the curl of f and dot product with k, that's exactly what we did yesterday. We showed a different version of Green's theorem that used the curl, right? And it was curl dot product with k. So in fact, if you take S to be the xy plane, or just some surface in the xy plane, then Stokes' theorem just becomes Green's theorem. So this is really a generalization of Green's theorem. Okay. Yeah, I want to show you an example. We can set it up. We'll set it up. We won't complete it. Because once you get to a certain stage, you're just computing double integrals, and we already know how to do that. Okay, so let's draw the following picture. So So I'm going to give you a vector field, and it'll be minus y squared, comma x, comma z squared. Okay, that doesn't sound so bad. Now, let's get this thing going on. What I'm thinking of here is having some cylinder, and I'm going to take a plane and cut through the cylinder, but I'm going to cut through it at an angle. So that when you cut through it, you get an ellipse. So I'm interested in this surface right here, called S, and the boundary we'll call C. So down at the bottom here, I just have a circle of radius 1. That's this thing. And actually, I can view this whole cylinder as just given by the two-dimensional function f of xy. F of x, y, z. What do I want now? I just want to allow every z value, basically. So I take this circle and let it stand up, and then I take a plane and slice it through. And the plane I'm going to use is y plus z equals 2. Okay. And we want to compute the surface integral, or the flux integral. Oh, no, I'm sorry. We want to do the other way. We want to compute the line integral around C. So I have this circle, this ellipse rather, that I call C, and I want to evaluate the line integral of this vector field. So if I use Stokes' theorem, it says I can write it as a surface integral. I think there's a dot. So there's an arrow. Okay. So I need to compute the curl of f. So I will save you the suspense because it's just a computation, right? This is curl of f is just the gradient cross product of f. And if you compute this out, you get just a k component. It's 1 plus 2y. Okay. Now, we saw over here that if you want to compute the surface integral, you can also compute it as a double integral. There's a missing dA. That's what happens when you try to prosecute the mob. You end up with a missing dA. Okay, so we're going to use this right here. So this is going to equal a double integral over d of the dot product 1 plus 2yk with, well, rx, and we can use x here, cross ry. Okay, so r, right, that's what's parameterizing the circle C. And, well, so I'll write it down. So r of xy is, I'll write it like this, xi plus yj plus 2 minus yk. Okay, so why is that? Well, the points on here, since it's given by y plus z equals 2, is once you know the x and y coordinates, I mean the x could be anything, then the y coordinate you give it, and then what z is given as 2 minus y. Okay, so that's where that parameterization is coming from. Okay. So if you, again, we lost our dA. If you compute the partial derivatives, take the cross product, and then do the dot product, you end up with, well, it turns out this bit, Rx cross Ry, just ends up being J plus K. And so the dot product isn't going to see the J term, because there's no J here. It's only going to see the K term, and that's a 1. So you actually end up getting just the double integral of 1 plus 2y dA. And this is now not such a bad thing if you convert to polar coordinates. You still need to do the d. Now what's the d, by the way, in this whole picture? Well, the d is what you project down onto on the xy plane, right? You have the surface up here, but remember how we did get the d? The d is what the s sits over. But this is just a circle, radius 1. You know how to parameterize that and write down d in polar form. So integrating this is not a problem. So use polar coordinates if you want to do this. And if you convert to polar coordinates and compute it, it actually ends up, after all the work, being pi. Amazingly. Okay, so I'm leaving out, of course, all the arithmetic details, but you guys know how to do this one now. But the important thing in all this is that computing this line integral traditionally is actually more challenging, right? If you don't use Stokes' theorem, just like with Green's theorem. But because you took this curl, and the curl ends up being really easy, just 1 plus 2y, the whole computation becomes easier. So let me make one more remark about these surface integrals in Stokes theorem. So, if S1 and S2 are both surfaces that satisfy all the requirements of Stokes theorem, then if you find the flux integral of the curl of f, then we know by Stokes theorem that this is equal. Oh, I should say these both. I forgot, of course, the key requirement in here. They satisfy the requirements of Stokes theorem and have the same boundary. C. Okay, and the analogy here is we had this independence of path theorem that said if you had a line that has the same endpoints and another line, I mean, has, well, of course, one line has 2 endpoints, another one has the same endpoints, then you could integrate over either and you get the same thing. Okay? So we're thinking the same thing here. The surface could be different. For instance, imagine if I take a ring. Right? I have a nice ring, and I dip it into soap. And then I pull it up. So now you have this film that goes across it. And now I go underneath it. Okay? And I blow up. What happens? You get a bubble and it kind of goes a nice spherical shape. What if instead I did it from above? Blows down. Okay? So you get 2 different surfaces, one that looks like this, one that looks like that. But their boundary is the same. It's that ring that I started with. Okay, so that's what I'm thinking of here. I have 2 surfaces, and they have the same boundary. Okay? And I call that boundary C. So I know by Stokes' theorem that if I integrate the curl, it's the same thing as the line integral over C. On the other hand, I also know that if I integrate over S2, the curl, I get the line integral over C. And so, in fact, you must get the same surface integrals, because they're both equal to the same line integral. So that's, instead of, it's a form of path independence again. Okay, so the very last thing is Gauss's theorem, Divergence Theorem. If you go to Russia, call it the Divergence Theorem. Because I think in Russia they named it after a Russian mathematician who also discovered it, I believe, independently of Gauss. And if you call it Gauss's theorem, I think they get mad. If you call it Divergence Theorem, they're okay. They call it, I can't remember the guy's name, is something like Ostrowski or Ostrowski or something like this. I'll look it up for you if you want. I'm sure a Russian watching is yelling at me right now. Okay. So this last bit is, let me just say, Stokes' theorem is good for turning a line integral into a surface integral where you have the curl here. The divergence theorem, Gauss's theorem, is good when you actually start with f here. You have a surface integral f and you want to transform it into something else. So in this case, what you're doing is, okay, we're going to start with some region in space called E. How do I draw this nicely? Okay, so you have some region in space. This is E. And for each point, right, we can draw the unit normal vectors going away. The surface of this thing, I want to call S. Okay, so the whole thing is E, but just the surface of it we call S. And we're making sure it has positive orientation, so the vectors are really going out, away from the inside. So the divergence theorem says, and of course there's hypotheses, but everything's usual. The vector field should have continuous partial derivatives on an open region containing E, and so forth. So if you want to evaluate the surface integral, or flux integral, what you can do is instead write it as a triple integral over the innards, E. And you have to replace F with the divergence, right? Which is again a kind of derivative. So if you read this backwards, you're thinking, if I want to integrate this derivative, I take the antiderivative and evaluate it on the boundary. S is the boundary of E. So they all are just the fundamental theorem of calculus in stronger and stronger versions. And this is, of course, dV. So a very quick example. Let's make f equal to zyx. Can we do the alphabet backwards?
No.
And I'll spot you zyx. You can sing it. ZYXWVUT SRQPONM LKJIHGF EDCBA. That's all, folks.
Can your kids do that yet?
Yeah. You guys are way behind.
You better catch up.
Okay. Let's let S be. Let's let S be just this sphere radius R. Then, we'll see. If I want to compute the surface integral, I can turn it into a triple integral by the divergence theorem. By the way, this right here is why it's called the divergence theorem. Okay, so I need to know the divergence of f. So remember, the divergence is just the dot product of the gradient with f. So this is pretty easy because you take the partial with respect to x of z, which is 0, plus the partial with respect to y of y, which is 1, plus the partial with respect to z of x, which is 0. So the whole thing is just 1.
So the x-coordinate is z, the y-coordinate is y, and the z-coordinate, okay.
Yeah.
And it's the same as back here, it was negative
Yeah.
y, so okay.
Exactly. Okay, so the surface integral of f ds is the triple integral of E1 dv. Oh, but remember when you put a 1 here, things are really, really nice. What are you doing? You're actually just computing the volume of this sphere. Right? So just the volume of this region E. E is, well, S is the surface of the sphere, but E is just the whole thing. So the volume is just 4/3 pi r. Let's see. Now, yeah, okay, that's good. So that's the divergence theorem. So of course, the moral of the whole course, you take 165, you take 166, you know how to differentiate, you know how to integrate. We saw that you could take functions of one variable and replace them with functions of 2 variables, 3 variables, 4 variables. And you could write down analogous ways of differentiating. We had partial differentiation. You could do a lot of the things you did for derivatives, like solve max and min problems. Right? When we looked at integration, we saw that we could go to double integration and triple integration to integrate over more complicated regions. And the definitions of those were always analogous to the versions that we originally had for single variable calculus. We then replaced scalar functions, right, which ate points in space and spit out numbers, and we replaced it by either vector functions or vector fields, which ate either just a real number or a point in space and spit out vectors. And we saw that we could just extend all those notions from single variable calculus all the way up to multivariable functions and all up to vector functions and vector fields. Right? Everything is done analogously, and all the definitions are the same every single time. Right? You just have to change, a little bit of your notation. Things get a little more complicated to write down, but in the end, the philosophy is exactly the same. So from one point of view, we haven't done anything new this entire semester, which is kind of depressing. Okay? But here's the flip side of that. Without doing anything new, we can solve a lot more problems than we could when we started in the semester. And if you open up an advanced physics text, and when I say advanced, I mean one that uses calculus, not a high school physics book. And those of you who are taking physics right now know that the calculus can get more involved in it. You don't need that many more new things. You just need to know where to apply them and how to apply them. And that's what physics is all about, is taking just a few tools from mathematics and applying them in a very broad range of problems. And then just using the same philosophy over and over to solve newer and newer problems. And now you can look at those advanced books and you know what they're talking about. When they write those double integrals down over S, right, these surface integrals, you know what they're talking about. You can work these things out. So you are now, by taking calculus, you put yourself into the elite of the world who have taken mathematics to a high level. By taking multivariable, you are now in the elite of the elite. There's very little in calculus that I could tell you about now that you wouldn't say, that makes sense based, I don't know what you're saying, but it makes sense compared to what we've seen before. So you should be very proud of that. Thank you for a wonderful semester. This will be our last lecture.
Oh, yeah.